Welcome to the third video on hypergeometric series, and if you have not followed this video series from the beginning, I will attach the playlist over here. Okay, so now in our previous video we verified that this series capture different interesting mathematical functions like log and arcsine x, sin x, cos x. So all of these functions can be encompassed within the hypergeometric series, basically ordinary hypergeometric series, where we have two variables in numerator, one of them in denominator, and then x or z or anything as such. So we basically verified this in previous video, and I have introduced okay, so the verification video is linked over here, and the introductory video of this function is also linked over here. Okay, so now in this video I will try to see how we get such functions for any known functions which are Taylor series. Yeah, so we have verified that this is in fact the hypergeometric series, but in this video I will show you how do we find such numbers inside the hypergeometric series which represents a function. So that is the goal of the video, and yeah, let me begin. So first of all, what we will do is we can basically write these functions in a Taylor expansion. Yeah, from sum going to 0 to infinity, some constants, let's say m of n, and then g to the power n. Okay, and like if you want to make this hypergeometric series with, let's say, constant a, b in numerator, c in denominator, and x as a variable, we know that hypergeometric series can be expanded as a sum going from n equals to 0 to infinity, a base n, b sub n by c sub n, and then x to the power n by n factorial. I have already explained about this notation in my previous video where I explained hypergeometric series, and this basically means a sub n means a rising factorial where we take product increasing the number, yeah, up to a plus n minus 1. Yeah, okay, so now basically if you want to compare these two, comparing it directly will be hard. Yeah, so what we can do is you can basically compare the ratios of tn plus 1 by tn from both the sums. We can, and because if these two series are same, the ratios should also be same. That's why we will try to compare the ratios of the tn plus 1 by tn from both of them and then equate it. So from here it will just be mn plus 1 by mn times g is equals to, from over here we will have okay, so n plus 1 term we will have product up to a plus n. Yeah, and nth term will have product up to a plus n minus 1. So a plus 1 n will remain over here, b plus n will remain, and c plus n. Similarly, x by n plus 1 will be remaining. So we can compare these two, yeah, and then try to find the a, b's, and c's, and that's how we will find a, b's, and c's, and then the hypersymmetric series. So let's do one example, and then that will make it further clarify. Yeah. So let me remove this and do an example over here. Okay, so we have ln of 1 plus g. Yeah, let me write it as a sum from n equals to 0 to infinity, minus 1 to the power n, g of g of n plus 1 by n plus 1. Now if we take the ratio t of n plus 1 by tn, what do we get? Minus 1, and then n plus 2 by n plus 1, yeah, and then g. Okay, and we know that this should be equal to a plus n b plus n by c plus n plus 1 times x. Okay, so for that, what we can basically do is we can put a equals to 1, yeah, c equals to 2, and we can also put b equals to 1, because if we put b equals to 1, these two will cancel out, yeah, and so we have n plus 1 by n plus 2, and we can put x as minus g, yeah. If we put x equals as minus g, then both of them will be same. So basically, our hypersymmetric series will now be hypersymmetric to 1, 2 in numerator, 1 in denominator, and a and 1, b is 1, c is 2, x is minus g, yeah. So but still, this may or may not be the answer, because we are just taking the ratios, yeah. That's why we are not sure about the first term, what that will be, or something like that. So for that, we just need to check the first term, and try to multiply here by some variables if needed. So basically, this hypersymmetric series uh, will start from g to the power 0, yeah. So over here it starts from n equals to 0. So first of all, we will have minus g to the power 0, yeah. So, and that is just 1, but log series starts from g itself. So over here we have n plus 1, yeah. So that's why we also need to multiply this by g, so that we have g to the power n plus 1. Now if we do this, what happens is, let me show you what happens. So basically, when you multiply this by g, so I'm going from n equals to 0 to infinity, 1 base n by 2 base n, so minus g to the power n, yeah. And so we have sum going from n equals to 1 to infinity. This is n factorial, and that cancels out. And now we have 1 by, this is n plus 1 factorial, so 1 by n plus 1, and minus 1 to the power n, and g to the power n plus 1. So only now this works, yeah. So that's why we needed to multiply this by g. We need to be careful about first terms even after comparing the ratios. That is the thing. Now let us go to the second problem. For 1 minus g to the power minus a. Okay. First of all, let's find a Taylor series, and we can find that using the binomial expansion. This is basically, so I'm going from n equals to 0 to infinity of minus a, choose n, minus g to the power n, yeah. And minus a, choose n, that will be minus a minus 1 up to minus a minus n plus 1 by n factorial, minus 1 to the power n, g to the power n. Now you can distribute negative 1 and negative 1s to each of them, and that makes it positive. So n equals to 0 to infinity, a plus 1 up to a plus n minus 1 by n factorial, and then minus g to the power n, yeah. So now after this, okay, no, not the minus sign, because minus sign is already distributed over here, and g to the power n. Now this is just okay. So now if we take the ratios, yeah, of tn plus 1 by tn, what do we get? Over there we will have a plus n, over here we will have n plus 1, over there we will have just z. Okay, so this needs to be equal with what? A plus n, b plus n by c plus n, n plus 1 times xn. That's why now what can we say? So basically we can put b and c both as 1, yeah. Yeah, instead of 1 any other things would also have worked, yeah, but for simplicity we can keep it 1, so that it cancels out. And we can put a as a itself, and we have n plus 1 already, and x as z. Yeah, so that's why it will be ordinary hypergeometric series of a comma 1 semicolon 1 semicolon z. Okay, so we found out for this as well. Yeah, so we have already done 2 of them. Now let's go to the arc sin x. Yeah, for arc sin x, let me do it over here, and that is 1 by 2 1 by 2 3 by 2 z square and z. Okay, so we basically have 1 by 2 1 by 2 3 by 2 z square and z. Now let's find out. We know the Taylor series for arc sin x is sum going from n equals to 0 to infinity 1 by 4 to the power n 2n choose n, and then um, let me write it z, arc sin z, and g to the power 2n plus 1 by 2n plus 1. Okay, so this is the Taylor series for arc sin x. Yeah, now we can simplify 2n choose n equals to 0 to infinity. I can write this as 2n factorial by n factorial g to the power 2n plus 1 by 2n plus 1. Okay, so now let's check the ratios of terms. Tn plus 1 by tn, what will that be? So 1 by 4 first, and then we will have 2n plus 1 2n plus 2. Yeah, and then over here we will have n plus 1 n plus 1, and over here we will have z square, and 2n plus 3 by 2n plus 1. Okay, so this is a long ratio. Now we can use 4 to cancel the 2's out here, and these 2 can be cancelled with each other. So we will have n plus 1 by 2 n plus 1 by 2, again over here also n plus 1 by 2, over here n plus 1 n plus 1 n plus 3 by 2 times g square. Is that it? Oh, wait. This is actually n plus 1, not n plus 1 by 2. This is actually n plus 1, yeah. Yeah. When we divide by 2, this actually becomes n plus 1. Now this cancels out. Now this simplifies nicely to the form that we want. So we basically want a plus n, b plus n by c plus n plus 1 by x. It looks like a hypersymmetric series was made for this function here. Now a is 1 by 2, b is also 1 by 2, c is 3 by 2, n plus 1 is there, and x is z square. So our hypersymmetric series should be 1 by 2, 1 by 2, 3 by 2, and g square. Okay, so but our first term doesn't have degree 0, it actually has degree 1. That's why we need to multiply by z as well. Okay, so this was the hypersymmetric series for arc sin x. Now let's go to the next problem for geometric series. Yeah, 1 1 1 and z. Okay, well, let's do it. For a geometric series 1 minus g to the power minus 1, it's actually ordinary hypergeometric series 1 1 1 g. Okay, so basically its series, we all know that it's sum from n equals to 0 to infinity z to the power n. Yeah, and the ratios will be tn plus 1 by tn will be just g itself. Now this should be equal to a plus n or b plus n by c plus n plus 1 times x. Now the best solution is to keep all of the ABCs 1 1 1, so they all cancel out. Yeah, we can put a equals to 1, b equals to 1, c equal. We can also put any other constant like 2 to 2, that will also work, but anything will work, so let's put 1, and x should be g. That's why in the first term is obviously of degree 0, and that's why it will be of no problem. And so the hypergeometric series will be 2 hypergeometric 1 1 1 semicolon 1 semicolon z. That is the answer. Let's go to the next problem. For e to the power x, it's dash 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 g. Okay, so for e to the power g, it's 2 hypergeometric 1 dash 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 g. Okay, its sum going from n equals to 1 to not 1 0 to infinity x to the power n by n factorial. So the ratio is x by n plus 1. Yeah, now this should be equals to uh, a plus n b plus n by c plus n plus 1 by uh, okay, so I should have written here g to the power n and then g to the power n by x. Okay, so in this case, like, we will not really be able to simplify by keeping a b c as 1 1 1. Yeah, that's why one of the possible ways that we can write hypergeometric series is just to say that it does not, we don't have anything, we don't have really a, we don't really have any b, we don't have any c. We can say that, and just uh, if you just let it to be as it is and x as g, so it will work. Yeah, that's why we write this as 2 hypergeometric 1. There's no a, no b, no c, and g. That was it. Now let's go to the next one, sine g. Dash dash 3 by 2 minus g square by 4 and g. Okay. Um, dash dash 3 by 4 minus g square by 4 and g. Was that it? 3 by 2 minus g square by g. 3 by 2. Okay, now let's do it. Now first of all, let's see the series expansion by sine of g. It's sum going from n equals to 0 to infinity. Okay, start with x. Yeah, and then what is that? Minus 1 to the power n x to the power 2n plus 1 by 2n plus 1. So basically it's not starting with 1, it's starting with x. So basically we will have this thing g over here at last. We have that sense right now. And let's find the ratio of tn plus 1 by tn. Basically get a minus 1, and then we get 1 by 2n plus 3 by 2n plus 1, and then x square. Okay, now we need to equate this with a plus n, b plus n. We can write this also as n plus 1 by 2 by n plus 1 by 3 sorry, this is factorial, and that's why there are some errors over here. Okay, if that's the factorial, it will be a different case. So minus x square by, now that will just be 2n plus 3, 2n plus 2. Yeah, now this should be equal to, this can be written as 1 by n plus 3 by 2, n plus 1, and then minus x square by 4. We know that this should be equal to a plus n, so b plus n by c plus n, n plus 1 times, again I wrote x over here, this was supposed to be z, supposed to be z, supposed to be z, over here x. Okay, so now if we compare both of them, we need to have, we can't really put a b as anything because they will never cancel out with denominators or something or anything like that. So we can't have any a, we can't have any b. We can have c as 3 by 2 and the other one is same, and x is minus g square by 4. So we can write this as hypergeometric series to 1 dash dash 3 by 2 comma minus g square by 4, and since the first term is not 1, it's g, that's why multiply this by z. Okay, so now we have our last function cos g dash dash 1 by 2 minus g square by 4. Okay, so it's dash dash 1 by 2 minus g square by 4. We know that Taylor series for cos of g is sum going from n equals to 0 to infinity, and then we will have minus 1 to the power n, g to the power 2n by 2n factorial, and the ratio will be tn plus 1 by tn, ratio will be minus 1, yeah, and then g square by 2n plus 2, 2n plus 1. Okay, now this can be written as minus g square by 4, 1 by n plus 1, and then n plus 1 by 2. Okay, yeah, and now we know that this should also be equals to a plus n, b plus n by c plus n, n plus 1 times x. You can't really have any a and b for this case, so no a, no b, and c equals to 1 by 2, yeah, and other is n plus 1 itself. Note that if we can put such values, we will try to put, but if we cannot, then we will not. X is equals to minus g square by 4. So we can write this as hypergeometric series to 1. A and b are nothing, and then c is 1 by 2, x is minus g square by 4. So that was it. So we found the hypergeometric series for all of these functions, comparing the Taylor series with the hypergeometric series. And yeah, also check for the first term if that's 1 or z. And that was it. In the next video, I'm going to show you an interesting some applications of hypergeometric series, like how it can be helpful to solve some integrals where there are basically no solutions. And yeah, I look forward to seeing you in that video. Thanks for watching. Look forward to seeing you again soon.